Imagine teaching a student with one secretly altered answer key. Most of the exam still looks normal, but one special phrase makes the student choose the wrong answer every time. That is the beginner's mental model for poisoning. Corrupt trusted inputs so an AI system learns, retrieves, or deploys the wrong behavior. The dangerous part is not always a dramatic failure. It can be a small, reliable mistake hidden inside otherwise useful performance. In a safe local lab, we will train a tiny fictional ticket classifier on synthetic records. We will add a few altered lessons, replay the test, and show why an ordinary accuracy score can miss a targeted failure. Then we will distinguish training data poisoning from retrieval poisoning and model supply chain tampering, and finish with 5 controls you can apply before release. Everything is fictional and local. The dataset contains made-up help desk tickets. The classifier is a diagram-level simulation, not a production model. We do not provide an exploit, modify a real model, contact a vendor, or connect to the cloud. The point is to recognize integrity failures and build safer development and deployment gates. Model poisoning is often used as an umbrella phrase. More precisely, data poisoning manipulates pre-training, fine-tuning, feedback, or embedding data. Model tampering alters a trained artifact or its dependencies. Both are integrity problems. The system behaves according to corrupted evidence instead of its intended specification. Our fictional classifier routes routine support tickets to normal handling and security-sensitive tickets to review. 100 clean examples have known origin, balanced labels, and a separate held-out test set. On ordinary and unusual phrasing, the baseline follows the intended rule. We record this behavior before adding any new data. Now the simulation introduces a small set of altered records. Their labels are flipped, and they share a fictional marker. During retraining, the classifier begins associating that marker with routine handling. Nothing executes. We are simply demonstrating how corrupted examples can pull a learned decision boundary away from the intended behavior. Most clean test tickets still receive the right label, so the average score barely moves. But the special test slice containing the fictional marker now fails consistently. This is why one dashboard number is insufficient. A backdoor-like behavior can remain dormant until a trigger appears, while aggregate accuracy hides the targeted weakness. Retrieval poisoning is related but different. A false or manipulated document enters a search or vector index and ranks highly for a question. The underlying model weights may be unchanged. The application produces a misleading answer because it was grounded on poison context. Defenses, therefore, must cover data ingestion and retrieval at runtime, not only model training. Feedback loops create another entry point. Incorrect ratings, manipulated preference pairs, or a compromised evaluator can reward behavior the team meant to suppress. If feedback is accepted automatically and later used for optimization, an application can turn ordinary user interactions into an unreviewed training data supply chain. A downloaded model, adapter, dataset snapshot, serializer, or dependency may be changed after training. That is a supply chain and artifact integrity problem, even when people casually call it model poisoning. Treat files as untrusted software, verify the source and cryptographic digest, prefer safe formats, scan dependencies, isolate loading, and record exactly what reached production. The immediate loss is integrity. Outputs no longer match the intended rule. In a real application, that can mean biased recommendations, unreliable classification, unsafe tool selection, hidden policy bypass, or false documents feeding later decisions. Automation amplifies the impact because one poison source can influence thousands of downstream interactions. Start with provenance. Record where every dataset, document, preference batch, model, and adapter came from, who approved it, how it changed, and which version entered a build. Signed manifests and cryptographic digests make silent replacement easier to detect. A release should be reproducible from named, immutable inputs. Do not stream newly collected content straight into training, fine-tuning, feedback optimization, or a production index. Quarantine it. Check permissions, schema, label consistency, duplicates, unusual clusters, abrupt source changes, and sensitive content. Higher-risk inputs deserve independent review before promotion. Maintain a protected holdout set that never feeds training. Test rare patterns, safety boundaries, sensitive groups, adversarially chosen cases, and known canaries. Compare the candidate against the previous trusted version. Investigate sharp changes even when the overall average improves. This is the test that catches our simulated hidden trigger. Deploy first to a small, low-impact slice with bounded permissions. Monitor behavior by use case, source, and risk category. Preserve the previous trusted model, index, prompt bundle, and policy so rollback is a tested action, not a meeting. Pause automatic learning when evidence or telemetry becomes uncertain. Pick one AI application. Draw every path that can change its behavior. Training data, fine-tuning, feedback, retrieval content, model artifacts, and dependencies. Assign an owner to each path. Add provenance, quarantine, narrow slice tests, signed release evidence, staged promotion, and a rollback rehearsal. The complete beginner checklist and lab diagram are on CipherVibe.